Hi, yet another important video from the course Analog Electronic Circuits. Continuation to the hybrid pi model, which comes in the concepts high frequency, transistor high frequency analysis. CE, short circuit current gain, CE, common emitter, short circuit current gain. And where do we start from? The analysis should start from the hybrid pi model, isn't it? So once again, we have to consider the hybrid pi model, which is guys, let this be the base and that virtual base B dash. So what comes in between over here? It's a R B B dash. The base spreading resistance comes over there. And what is over here? Between what resistance comes over here between the virtual base B dash and C? It's a R B dash C, isn't it? And CE, common emitter configuration, and so emitter will be the common point. Emitter configuration, common emitter configuration. Emitter is common to both input and output, isn't it? So this will be the emitter part here. And what is that resistance comes in between the forward bias junction between B dash and emitter? It's a R B dash E, isn't it? And that voltage measured over here is V B dash E, right over here, this one. And IB will be flowing over here. B will be flowing over here, right? And what else did we forget? Yeah, many components yet to come. We have a RCE resistance between collector and emitter, and VCE is measured over here, isn't it? We have that VCE measured over here, and this will be the VBE over here, right? Not only this, we have a current generator IC, and we have a current generator over here. What is that? It's a GMVB-E, isn't it? So that one. And not only this, because of the forward bias and reverse bias junctions, we have capacitances, capacitive effects in the transistor, which has to be reflected over here. What is that? We have a capacitance over here, which is denoted as C B dash between emitter, isn't it? E, and another capacitive effect between the virtual base B dash and the collector, reverse bias junction. Capacitive effect across the reverse bias junction, that is C B dash C, or simply CC, and this will be simply CE, isn't it? So guys, yeah, this is the complete hybrid pi model, and we have to start the analysis from this point. And here, this resistance are this one, this resistance and this capacitance. These two elements are in common between the input and output. The analysis will be tedious, I repeat. These two components, RB dash C and CB dash C. This resistance and this capacitance are common between input and output. The analysis will be somewhat tedious. So there is a convenient approach. We can take it out. Guys, this resistance and this capacitance could be removed from there. A part of this resistance can be placed in the input, and a part of this resistance can be placed in the output. Still, the characteristics of the circuit doesn't change. I repeat, this resistance and this capacitance can be removed from here. Okay, this can be removed from here, and a part of RB-C could be placed in the input. In the same way, a part of this CB-C could be placed in the input. So what amount is the question? What amount of what part of this one should be placed in the input and what part of that one should be placed in the output is the question. Okay, that is which is given by Miller's theorem. Yeah, Miller's theorem suggests what amount of resistance should be placed in the input and output, and what amount of capacitance to be, what amount of parameter should be placed in the input and the output, which is common between input and output. Right? So Miller's theorem, what does Miller's theorem says is considering this one, a small two-port network, very much similar that transistor, okay, the transistor which is common input and output, right? So what do we have? We have V1 over here and we have V2 over here. V1 and V2, I1 and I2, you may be familiar when you do that hybrid parameters in two-port networks here. And what is this? We have I1 over here and I2. Let's suppose, guys, we have a resistance which is common to both input and output over here, resistance R, right? So now for the analysis part, if we have a component which is in common between output and input, it will be tedious. Okay, we can go out, we can do the analysis, but that will be tedious. According to Miller's theorem, we have a simple approach that a part of this one, break it away and put it some part of this one in the input, put this one some part of this in the output. So that's suggested by Miller's theorem, right? So what amount can be analyzed from here? So guys, according to network theory, what will be I1? Current I1 can be written as I1 is equal to I1 due to V1, right? So V1 minus V2 by R. Clear? So guys, taking out V1 as common from here and here. So V1 as common from here. So we have 1 minus V2 by V1 and R as it is. Okay. So this ratio, a small change over here. I1 from here by V1, which is equal to 1 minus, guys, make use of your common sense. What is this ratio? V2 by V1? V2 output voltage by input voltage. It's a voltage gain, so that will be AV, voltage gain AV by R. Okay, so the reciprocal of this one, V1 by I1, which is equal to R1, which is very much precisely like Rn as far as our discussion is concerned. Rn, which is equal to R by 1 minus AV. So guys, this is the amount of resistance, this is the amount of this part that should be placed, take it away, pull it away, and R upon 1 minus AV times resistance is placed in the input, and that doesn't change the characteristics of the circuit. Yeah, so this is the amount of input resistance. Okay, take this away, and what amount of resistance has to be placed over here so that the circuit characteristics doesn't change? RB dash C upon 1 minus AV times resistance to be placed over here, and it will be the characteristics doesn't change. So what amount of this parameter should be placed in the output? Writing again, what is the expression for I2? I2 is given as V2 minus V1 by R, isn't it? So taking out V2 has come from here and here. So what do we have? V2 has come out. We are left with 1 minus V1 by V2 upon R. So that ratio I2 by V2 will be equal to 1 minus 1 by AV. This is the reciprocal, right? By R, and we are in search of V2 by I2, which is equal to R2, which is equal to R0, for supposing that resistance which has to be placed at the output is given by R by 1 minus 1 by AV times, or simply R into what? This, simplifying this one, we have AV over here which goes up, AV by AV minus 1. So this is the amount of resistance, if at all. This is the amount of resistance that can be taken, removed from here, and this is the amount of resistance that can be placed in the output. These are the important equations suggested by that Miller's theorem. According to Miller's theorem, this is the amount of resistance to be placed in the input, removing this one, and this is the amount of the output that should be placed over here at the output. Okay, this is applicable for the resistance and capacitance. And guys, to be more clear, we consider the reactance of the capacitance that to be placed over here. The reactance we start from, and yeah, remember that resistance to be placed over here is named as Miller's resistance. If at all this capacitance is removed from here, and a part of this capacitance to be placed over here, that component that has got the name Miller's capacitance, Miller's resistance. Right? Did I confuse you? I'm repeating. So we'll have to, it's in common between input and output, isn't it? As I said, the analysis will be tedious if you go ahead. Okay, we can solve, but that will be tedious. Why the hell going for a tedious job when we have another simple approach for the analysis? So what according to Miller's theorem is, this can be removed from here, a part of the capacitance can be placed over here and here, and the analysis can be carried out so that the characteristics of the circuit doesn't change, won't change, right? And that capacitance which is placed in the input and output has got a name, Miller's capacitance, Miller's resistance, etc. Right, making use of Miller's theorem, and so that has got the name. Right, so remember, this is the amount of the resistance that should be, this is the amount of the component which is in common to be placed in the output, and this amount of the component should be placed in the input, so that the characteristics of the circuit doesn't change. Keep that in mind. We have to make use of this one over here. Why? Because CE, short circuit, this can be shorted, and we don't need that output part, etc. Let me go on with the analysis. Okay, I'll give you a clarity of what is not needed and what is needed. So guys, this is the one. Okay, so, and yeah, yet another important point that has to be underlined during this discussion is this resistance RB dash E, which is between the virtual base B dash and emitter, is that resistance comes into existence across the forward bias junction, because emitter junction should be forward biased and collector junction should be reverse biased, isn't it? So in that case, practically this value will be in terms of kilo ohms, this value will be in terms of mega ohms practically. Check the data sheet, so that what I want to say is, as far as this analysis is concerned, this resistance is very high when compared to this one. Even the half part will be very higher when compared to this one. Even the half part of this one will be very high when compared to this one. Okay, so remove this one, right? According to Miller's theorem, I have started applying that Miller's theorem. Why? Because I need to go further with the analysis, and I wanted to make the analysis simpler. So what amount of resistance should be placed over here? Here, it's here. Okay, so this one, I need to place a resistance. No, it would be better if I go with another color. Yeah, I need to place this resistance. What amount it should be? That resistance, it was RB dash C, isn't it? By 1 minus AV times I need to plug in over here, if at all I remove this one. And over here I need to go for another resistance over here. Okay, and that resistance value should be RB dash C into AV by 1 minus AV times. Right, so this one, and practically this resistance is very high. This, even if there is a reduction over here, this resistance is very high when compared to this resistance. Okay, we are placing this amount of resistance, RB dash C by 1 minus AV times of resistance is placed over here, which is in shunt with RB dash E. This value is very much, when compared to this one, when compared to this RB dash E, this is very high. Okay, and from the fundamentals of resistances, two resistances in shunt with each other, a higher value and a lower value, the resultant resistance will be equal to the lower value resistance, isn't it? So in that case, guys, I repeat, this RB dash C by 1 minus AV, we can prove that in the numericals. Okay, this value is very much higher when compared to this one, and this resistance are in shunt with each other, and the resultant will be equal to the lower value. And so in that case, I repeat, in that case, making use of that fact, we don't need this anymore, right? So don't get confused, we don't need this resistance over here. Why? Because this resistance value is very much compared to this one, and when two resistances are in shunt with each other with a higher and lower value, the resultant will be equal to the lower value resistance. So we don't need this anymore over here. Okay, it has been split, it's placed over here, but the resultant will be equal to this, approximately equal to this one only. So we don't need this one in this case. Okay, so that, and yeah, I have placed this much of amount of resistance over here. That's another case. Now what about the capacitance? This capacitance also should be removed, and the question is what amount of capacitance to be placed over in the input and what amount of this one to be placed in the output, right? So guys, straight away not the capacitance, but we are talking about the capacitor over here. It has some reactance considering, and I've told you another name, that capacitance or that element has to be placed over here. If you talk about capacitor, that amount of capacitance which comes over here has got the name Miller's capacitance, CM, Miller's capacitance Cm, which is equal to how much? The question is what amount of capacitance to be placed over here. This doesn't give us any particular information, but considering the reactance X Cm will give us the information what amount of capacitance to be placed over here, right? So writing the expression for that amount, it's a X C for simplicity, okay, C B dash C, that could be C for simplicity. Why? Because we can omit that B dash, the centric, B dash is the centric of all these analysis, by 1 minus AV times, right, according to Miller's theorem. It has got some reactance, and what amount of reactance should come into the picture over here? Reactance by 1 minus AV times. Hold on. So what is AV? What is AV? It's a voltage gain, isn't it? And guys, IC is flowing over this side, and the load resistance should be over here, isn't it? The load resistance should be existing over here, RL, and IL flowing over this side. So what do we have from, what can be concluded from this an arrangement? IL will be equal to minus IC against each other, right? And VCE will be equal to IL RL, which is equal to minus IC RL. Is that clear? This one, VCE is equal to IL RL. IL and IC are against each other, so minus IC, this is L, this is C, okay, don't get confused, minus IC RL. And guys, centric with B dash, so we will be considering B dash as input over in this case, okay. So AV, voltage gain AV is equal to V output voltage VCE by VB dash E, right? We see more clearly, more precisely, VB dash E, right? And so which gives us so guys, what's that? VCE could be plugged in with this one. What's that amount? Minus IC RL by VB dash E. Guys, from the previous knowledge, what is this ratio? IC by VB dash E. Why? Because we have IC is equal to GM VB dash E, isn't it? So IC by VB dash E could be plugged in with GM transconductance. So we have another equation for that. AV, plugging in the value of this ratio, which is this one, minus GM RL, right? Now plug this one over here. So which will be equal to XCC, that one, which is common between this point and this point, by 1 negative, that becomes positive, into GM RL, right? That's the amount. Yeah, hold on, we aren't finished yet. So XCM can be written as 1 by J omega CM. Now this is the value we are in search of, which is equal to XCC, 1 by J omega CC by 1 plus GM RL. Okay, so a small simplification, this comes down, isn't it? Rearranging this one, this comes down. So what do we have? J omega CC into 1 plus GM RL. What is RL over here? The load resistance, okay. So GM, right? So guys, this is clear, isn't it? So this will be equal to this, and what will be the reciprocal? This is equal to this. What will be the reciprocal? J omega CM will be equal to J omega CC into 1 plus GM RL. Okay, so guys, this gets cancelled, and so let me erase this away, okay, for my convenience. I'm confused, so this gets cancelled, so I'm erasing this away. So guys, CM, we are in search of that CM, which is equal to CC into 1 plus GM RL. This is the amount of capacitance that has to be placed over here. making use of Miller's theorem. Yeah, Miller's capacitance, this comes over here. Okay, so guys, remember this one. Remember, this is a very important equation which has to be made use in two analysis. Over here, CE short circuit current gain, and also with CE current gain of a common emitter amplifier with load resistance. We short circuit this one, analysis carried out, and we place this RL, and then we'll have to make use of this expression in both the analysis. Okay, CE short circuit current gain, short circuit in the sense, guys, in the sense here we have a IL will be flowing, we have a short circuit over here, we have a, this is shorted, in the sense RL is removed making 0, in the sense this is 0. Okay, this is 0 as far as this analysis is concerned. We'll make use of this expression, the next one, when there exists a load resistance. Okay, CE short circuit current gain, so RL is made 0, RL is 0, so we don't have this one, we don't have this one. So this is the amount of capacitance which comes over here in CE short circuit current gain. We can remove this one according to Miller's theorem, this could be removed. Okay, and Miller's capacitance, what amount of Miller's capacitance according to this analysis? CC, that CC comes over here, C B dash C for simplicity, although analysis is B dash centric, so we can omit that one, C, and C B dash E, C, E, right, this one. And another point is, guys, yeah, even we have a capacitor over here. Okay, we have to place that capacitor over here, a part of capacitor. I didn't focus much on that one. Why? Because this is short circuited and nothing stands in front of this one. Whatever capacitive effect, resistive effect becomes 0 in front of which is in shunt with this short circuit, isn't it? So short circuit, nothing stands in front of that one here, so this resistance also doesn't exist, becomes invalid. Even that resistance which is part of this one which is placed over here becomes invalid, and that capacitance also, and we have simply this one. Okay, we have simply that that's a circuit. Okay, so guys, we are in search of current gain, short circuit current gain, isn't it? Short circuit current gain, and yeah, we'll make use of all these, this one, and RB dash E alone exists over here. Why? Because okay, this part of resistance is placed over here, but still that will be very high when compared to this one, that can be neglected with this one. So these two are in shunt with each other, right? CE and CC are shunt with each other, and so parallel capacitors can be replaced like this one. Parallel capacitors can be replaced like this capacitors, and CE, so guys, where should I write down? CE plus CC when two capacitors are in shunt with each other. So this is the complete reduced form of hybrid pi model making use of Miller's theorem for CE short circuit current gain. If at all this wasn't shorted, we have all that parameters. Our CE would have come into the picture, and that Miller's resistance over here that will be existing, that will be for the next analysis. Okay, with resistive load, CE current gain with resistive load. Yeah, we have to, and making use of this one. Okay, CM is equal to CC into 1 plus GMRL times, right? So we'll have to make use of this, and we are in search of, what is that? Current gain, isn't it? Current gain AI is equal to IL by IB, which is equal to minus IC by IB. Okay, minus IC by IB. Why? Because these two are against each other. So AI takes another form which is equal to, is IC is this one, isn't it? AI equal to minus IC could be this one, GM V B dash E by IB. Okay, GM V B dash E by IB. Now we have to find out this. Okay, let's see what happens. Let's see what happens. Now guys, hope you understood the reduction. So what is this? We need to evaluate Z. Okay, the resistance is in shunt with this one. IB is flowing over this side, and we need to evaluate this drop. So for that we need to evaluate Z. What is Z over there? Z is the parallel combination of this one. So the parallel combination of RB dash E parallel to XCE plus CC. Z, right? We are evaluating the impedance, right? So that will be Z will be equal to, what is that? RB dash E into 1 by J omega CE plus CC. Okay, the parallel combination, right? By RB dash E plus 1 by J omega CE plus CC. Okay, so this simplifying this one, guys, simplifying this one, this ratios, what do we have? In the denominator part we have RB dash E by J omega CE plus CC. Okay, and over here the LCM will be J omega CE plus CC, and cross multiplying this one, this ratio, cross multiplying this one, 1 plus J omega RB dash E into CE plus CC will be the simplification. Okay, so guys, something gets cancelled over here, this denominator over here and this denominator over here gets cancelled, and the impedance Z, this impedance will be equal to this, right, with the RB dash E being over here. This is the impedance Z, right? And from this arrangement here, what will be this one? From this arrangement, the voltage drop VB dash E could be written as IB into Z, isn't it? And that ratio VB dash E by IB will be equal to Z, right? So which Z? This is the value of Z we are talking about, right? So this is the one. Z is equal to that, so remember that one. And this Z value, which is equal to this entire, this ratio being Z, that has to be somewhere else. Yeah, let's see where that can be plugged in. Going back to this one, guys, AI will be equal to minus GM VB dash E by IB, isn't it? So we have that ratio, we have this ratio which is equal to Z, still which is equal to this one. Okay, so this is one, guys. I'm gonna erase this one, make a note. This ratio, this by this is equal to Z, that Z which is equal to this one, I'm gonna plug in directly, right? So here I'm gonna erase this one, that ratio will be equal to, is equal to Z, and that Z value is this, and I'm replacing over here RB dash E by 1 plus J omega RB dash E into CE plus CC. Okay, so here this is the one. And so guys, from the previous knowledge of analysis of a high frequency, hybrid pi model, this product is equal to, what is that? GM is equal to this product is equal to HFE. Check this product, GM into RB dash E is equal to, I am erasing itself here itself, I am not writing that again. This GM RB dash E is equal to HFE. We have derived this one. Go for the previous derivations. Okay, this one, right? So guys, not only this is the expression for AI. No, we are in search of something else. We are in search of something else. I forgot to tell you in the beginning itself. For a RC network, for a RNC network, It can be proved that, I don't have time now, it can be proved that for R and C, for a network with a resistance and capacitance, we can prove that if the frequency of that network will be 1 by 2, what is that, 2 pi RC. The frequency of oscillations of a RC network can be proved. Yeah guys, we have a proof for this one. Search for that one, right? Frequency F is equal to 2 pi resistance in whatever form it may be into capacitance in whatever form it may be, right? And if at all we have 2 pi RC, that could be plugged in with 1 by F of that frequency, the reciprocal, right? So here, come over here. So guys, omega, from the beginning, from your previous grades itself, you may be knowing omega, the radians, frequency in radians, 2 pi F, isn't it? So that same value of omega over here. Okay, so minus HFE by 1 plus J, omega is plugged in with that one, radians, frequency in radians, 2 pi F R B dash E into CE plus CC. Okay, so guys, watch carefully. Other than this frequency, we have another frequency in this expression. Other than this frequency F, okay, it came into picture with this omega, omega equal to 2 pi, that's okay. But other than this frequency here, we have another frequency over there. See this, come back to this one. F is equal to 1 by 2 pi RC for a RC network. We have a proof for that one, try for that one, right? F is equal to 1 by 2 pi RC. R may be in any form, C may be in any form. It's a 2 pi here, 2 pi R and C. 2 pi R and C, that will be equal to 1 by F. Here, F as it is, 2 pi RC, that will be equal to 1 by F. So a small rearrangement over here, modification, HFE by 1 plus J, this F as it is, 2 pi RC equal to 1 by F, 2 pi RC, which is equal to, as another notation over here, F beta. Small change in the frequency, it cannot be F and F, right? That will be a confusion over here, which is the expression for AI. And the magnitude of AI will be, that will be HFE by under root 1 plus F by F beta. We need to have a definition for this F beta, right? This is the working frequency. If you are here, you might have had a knowledge about the similar graph sheet. Different values of frequencies as we go on this one, frequency, and you may be asked by your teacher in the lab to evaluate the bandwidth, right? So bandwidth, this frequency minus this, that. This is the working different frequencies. Frequency 100 Hertz, 200 Hertz, megahertz, like that. This is a fixed value, but this is the working frequency, right? From this one here itself, we can get the definition for F beta, that at F is equal to F beta, right? This working frequency is equal to F beta. Guys, I'm very sorry, this should be square, right? Because it's a magnitude, this one. A plus JB, the magnitude will be under root A square plus B square, right? So we don't like 1 square, it's 1, so I forgot to mention the square over here. I'm very sorry, we need to have a square over here. Okay, at F is equal to F beta, let's see what happens to the gain, which is equal to HFE by under root 1 plus F beta by F beta whole square. Guys, what is this? It's a 1. F beta in the denominator, in the numerator gets cancelled, it's a 1. So what do we have? HFE by under root, how much? 1 plus 1 squared, so 2 root. right? So if from here itself we can have the definition for f beta. F beta, what? Where do I have to write down? F beta, what is that f beta? Guys, the expression for f beta, what was that? 1 by 2 pi r b dash e into c e plus c c, isn't it? So this value of this frequency is the frequency at which the gain is reduced to 1 by root 2 times, or else 0.707 HFE times. So that's the expression, that's the definition for f beta. The value, the frequency at which the current gain reduces to 1 by root 2 times. HFE is reduced to 1 by root 2 times, right? 0.70 of the final value, HFE. So that's the expression for, that's the definition for f beta, right? This has to be proved, okay? AI is equal to this one, and we should go in search of another frequency. Not only f beta, we have to evaluate another frequency, that's that frequency here, this frequency, what is that? F beta. F beta is the frequency at which AI is reduced to 1 by root 2 times. And we have another frequency, that frequency which makes the current gain equal to unity. Yeah, let's see that. At f is equal to ft, let's say, magnitude AI is equal to unity, which is equal to HFE by under root 1 plus, now this f is plugged in with f of t, so f of t by f beta whole square, right? Guys, practically when we do the numericals, we can prove that this is very much higher than this one, okay? This value, we will have some value, it will be in terms of kilohertz or megahertz or like that, okay? Yeah, finally this value is very much higher when compared to this one, so this becomes it cannot stand in front of that one. So guys, this gets cancelled, okay? So that gets cancelled, and here that's for f beta, and we are in search of another frequency ft at which the magnitude gain becomes unity, okay? So what we have is a HFE by ft upon f beta is equal to 1. So this goes up, right? This goes up, this goes to that side, which implies what is that? Ft over here, this goes up, which is equal to HFE f beta. Guys, you have to conclude with this one. Ft is equal to HFE into f beta. It will be asked to derive the expression, show the relationship between ft and f beta. You have to start from the short circuit current gain, from the hybrid pi model and reduction with the Miller's theorem, etc. Right? So you have to show this one, and you have to produce the relationship between ft. You got to define what is ft, and then you have to show the relationship between ft and f beta. Finally, you have to reach this one, right? Hope you understood the analysis. Thanks for watching.